Okay, so I actually brought along with me a processor. So this is what I'm going to be talking about today, at least this morning. And you can come look at it later if you want. But the idea is there is a lot going on in the processor that we normally don't think about. But if we start to understand the basic components, what's happening, what parts are inside, how different generations of processors are different from each other, then we can begin to utilize that information to write better code, do more efficient simulations, and just have a better understanding of how programming works in general. Let's see if this is working. So I want to get across the main points here right at the start. So if there's nothing else that you remember, just remember these things. If we understand the hardware, like I said, we can write better software. And faster data, or faster code, means more data and stronger results. So this really does matter for scientific progress. It also means that we can study harder problems than we were able to before, and we can simulate larger systems. So rather than wait 5 years for better computers, faster processors, more cores, you can get the same thing now if you're smart about it and use some tricks. And of course, it also means less electricity wasted and less money spent. Even though that's not something that you really notice, maybe as a student or as a researcher, somebody's paying for it. And so it's worth reducing costs if you can. So let's look at the processor. So here we have an example of an i7 die. And you can see that there are 8 cores here. There's a shared cache that's level 3. There's a memory controller, and then you have a whole bunch of other stuff which supports the CPU, but isn't necessarily within the core. So when we're purchasing a processor, some of you might have built computers before, and you're going through online and you're trying to compare which one should I buy. You normally think about the number of cores, the clock speed, maybe the cache sizes or the PCI lanes if you're interested in graphics cards. But you should also think about some other things. What generation is it? Because that will determine which instructions are available to you. So newer processors are not just faster, they don't just have more cores, but they actually can do different things. They have different circuits inside them. You also want to think about the pipeline depth. So this has to do with how many things can execute nearly in parallel, and I'll talk more about that. You want to think about the memory speed. So if you're purchasing really fast RAM, you need to make sure that the CPU can support that. And of course, the power, which affects the cost to use it. So if you buy something that is very efficient, then if it's for your personal computer, it will reduce your electricity bill at the end of the month. So what's actually happening inside one of these cores? Well, as I mentioned, there's this level 3 cache, which serves all of the cores. You don't need to know everything. You don't need to be an expert on this in order to get something out of this presentation. But I want to sort of go through the steps of what's happening when you're running a program. So what's going to happen is you have your level 1 and level 2 caches, specifically the instruction caches. And what's happening is when you compile your program into binary, it's just a list of operations. And this gets loaded into a very small cache. Separate from that is your data cache. This is the data that you're generating, the variables in your program, all of that. And so what's happening is the CPU is going to be going through these instructions, decoding them. It might break them up into smaller instructions called micro operations. And I'll talk about that in a moment. It's going to perhaps reorder them. So if certain operations are independent from each other, then they will be able to execute more efficiently if the processor is able to reorder them in that way. So that's what's happening over here with this register renamer and also at the unified reservation station. So what you'll notice here is that you have multiple ports, 0 through 5 here. So if 2 instructions are going through different ports, they do not block each other. So that means that they can execute nearly simultaneously, and this is called instruction level parallelism. Importantly, different ports do different things. So one of the things that the processor will do is try and reorder things so that you don't have many things going through the same port at the same time. There are all these, the TLB is the translation look-aside buffer, and what this does is it keeps track of where things are in memory. So if something is not in the cache, it will be able to look up where it is and go fetch it for you. So I don't want to focus too much on this, but the point is there's a lot happening, and you want to start thinking about what your operations are, what the instructions are. Now, if you're looking at the registers themselves, this is the very lowest level of memory. So you have your RAM, you have your caches, and then ultimately you have your registers. Now in 64-bit systems, these will be 64 bits. You also have, so you have your general purpose registers, which is where you might store integers. You have your floating point registers, where you'll store floats or doubles. But then you have all of these vector registers as well. And normally you don't think about these. You don't think about, when you're writing a program, how are you going to vectorize your code? And so we'll talk about that today, how you vectorize code and how you utilize this, because clearly there's a lot of them. And depending on the generation of processor you have, you can see over here, if you have something like a Skylake processor or even a Haswell processor, you have access to a lot of these. But they're not necessarily worth using all of the time because they're located in a different spot on the chip, on the die. So the instructions themselves are not all equal. I've listed some here, and these are measurements performed by a guy named Agnerfog. And there's this PDF called instruction tables that you can look up online. And it's absolutely brilliant because for almost every processor you can think of, you can look up how long each instruction takes, and this guy has measured it. And so you can see immediately that things like moving, if you take data and move it from one register to another, or if you add things or even multiply, it's very efficient. And the reason for this is because computers have been doing these operations forever, and it's really important for them to be fast. So they have dedicated circuits that do this. Now I mentioned that there are micro operations, and what this means is that while these instructions are what you would see in the assembly code after you compile it, they do get broken up sometimes. So it might be a sequence of operations, and this gets closer to the hardware level in terms of what's happening in the actual circuits. So for instance, division is way more expensive than multiplication. That's something to keep in mind. If you're doing any bitwise operations, so this would be a logical operation, AND, OR, XOR, that's going to be very efficient. If you're doing something like higher level, like trigonometry, cosine, or sine and cosine, you can end up taking dozens or hundreds of clock cycles to do that. I should mention here, the measurements that you use are called the latency and the throughput, or the reciprocal throughput. And what these tell you are how fast the processor can process these instructions and have the data ready at the other end. So then this gets back to the ports themselves. If you are able to stack instructions in the proper way, then they won't be blocking each other. So for instance, the move operation or the addition operation has a latency of 1, so it only takes 1 clock cycle, but you can do 4 of them per cycle. Okay. So this has to do with the fact that you have this instruction level parallelism. I've also posted these vector operations here, and you can see that they are fairly similar to the regular operations, but what you have to take into account is that you have to move things into those registers, and that can be expensive. So you only want to vectorize your code if the work that you're doing in those registers is going to greatly supersede the amount of time that it takes to move things back and forth. If any of you are familiar with GPU programming, then this will be a familiar concept. You want the operation on the GPU to take much longer than the transfer time of the data.
I have a question.
Yeah.
I noticed for the square root, it only takes one micro operation, but then it has a very large latency, and everything else seems to be pretty much in line, but it's specifically like the square root that has like a very disproportionate latency.
So the micro operation doesn't necessarily have to do with clock cycles. It's a reflection of what's happening, the way the hardware is laid out. Okay. So yeah, that's an important point to note. The other thing related to that is that for these vector operations, those registers are maybe 256 or 512 bits instead of 64. So even though it takes one clock cycle, you're going through 4 times or 8 times the amount of data that you might otherwise. Yeah.
Sorry, can you clarify what you mean by vector? Are you referring to like a C++ vector?
No. So I'm referring to, if we go back, I'm referring to data in these registers. So you have to use specific instructions, and I'll show you how to do this later, but you have to specifically tell it to use those registers. Now, let's be real. A lot of us use compilers. We don't write in assembly. If you are using G++ or GCC or whatever else, a lot of times the compiler is able to recognize when it should use these registers. So it's not like they're there but they're never used. In many, many applications, they are used. You just have the ability to also explicitly use them, which you don't necessarily do.
So can I see?
Yeah.
So I played with this a bit, and you can, by using even the CD code, you can use forensics to force it to vector operations. And then you can compare it to what the compiler does. And a lot of the compilers will actually tell you, what happened when they entered the vector. They'll say, no, I decided not to. And then you can force it to, and my experience is that usually it runs much slower when you force it to vectorize. And the compiler was smart to not try to vectorize the code.
That's right. That's right. That's a very difficult part of this, is that there is no rule for when to do one thing or another. And in many cases, in my experience, in everybody's experience, the only way to know what to do is to try option A and try option B and benchmark them and see what you get. But at least you want to know the full range of options that you have. So I mentioned that because of these different ports, we have this instruction level parallelism. So in the unified reservation station, they use different ports, they don't block each other, and there's this out of order execution unit which will reorder the instructions dynamically even in order to maximize this behavior. So if your code is running and it's a very long simulation, then as it's running, the processor will be able to find the patterns in the instructions and optimize this. As I mentioned, the compiler is very helpful with this. But at the same time, if you write code which explicitly encourages this, then you can boost performance. So let's look at a very simple example. So suppose you're just doing some for loop. So here I've chosen to do some XOR operation. If you're familiar with it, it's just a logical operation that similar to AND or OR. You could also read this as plus equals if you don't know what that is. But the point is, when you're doing a loop, you can choose to unroll it. And what that means is that instead of doing one of these statements and incrementing by one, you can explicitly write out 4 of them or more. It looks really obvious. It's not some crazy trick. But what you see, and this is with no optimizations on the compiler. Okay, so if you, normally the compiler might be able to tell to do this. It might not though, based on what this n is. So that's very important. You might know something that the compiler doesn't. if you unroll it with 4 times, then you do see about 2 times speed up. If you do 8 times unrolling, you don't get very much more.
Yeah, notice it's a log scale on the left.
It's a log-log scale. That's right. Log-log scale. So yeah, I just plotted this for some range of data sizes, and you can see that you get some basic speed up. So this is something to think about.
Why is that? So why is it speeding up?
Because it's able to, when it's unrolling the loop, it's able to take advantage of this instruction level parallelism, and the instructions are able to, those 4 instructions are able to execute independently.
So the different ports that you showed.
That's right. That's right. So if you were able to write it in assembly as well, then you could specifically tell it which registers to use. And so that's, to some extent, that's what's happening, is you're telling it to use different registers. Yes?
Is there a reason why if you combine 8 of them, it doesn't speed up that much instead of 4?
Because in this case, it has to do as well with the cache occupancy. So like here, you could obviously unroll the loop fully. That would be the extreme case. But there are only a certain number of registers and a certain number of ports. And so after a certain amount of unrolling, you're not going to get any more out of it. So that's sort of the simple answer to that. So another thing I want to mention is the clock speed is not always what it might seem. If you're purchasing a processor, this is probably one of the things you look at, along with how many cores. What you're able to do, though, they publish this data. It's called, for this one, the Intel Xeon processor, Scalable Family Specification Update. So the Xeon scalable processors are the newest things that are used in supercomputers these days. And so over here you see different models, but let's just look at the first one for now, if you can see this. So this has 28 cores, and what you see is that the base clock speed is going to be 2.5 gigahertz, and the maximum turbo speed is going to be 3.8 gigahertz. But that's only if you're using 1 core and none of these vector registers, no fancy tricks. If you are using more cores, it is going to slow down all the way down to 3.2 gigahertz. And that might not seem like a lot. 3.2 is still a lot better than 2.5. But the other thing to keep in mind is that this is the most expensive processor that you can purchase, and it's about $10,000. And because it's scalable, that means you should buy 2 or 4 of them for your computer. So in general, it won't be that good. So the other thing is, if you do choose to use the vector registers, it's even worse. The base clock speed over here also decreases. So before it was 2.5, now it's 2.1. And again, when you use more cores, it slows down. In this case, you have so this is if you use 256-bit vector registers. If you use the full 512 bits that are available, it slows down even more, down to 1.7. And so you might be asking, how does it know which clock speed to use? When does it use one or the other? And the answer is, it mostly has to do with heat, okay, and power that's available, but mostly heat. So there are little sensors all over the chip, things that we don't have access to, but they have access to in testing. And it makes sure that the clock speed is the same on different parts of the chip. And so if the clock speed starts to vary at different points, that generally means that it's going to, it's overheating in one portion, and so it'll slow down a little bit. So it's not like it's measuring the heat dynamically, but during testing they will have a good idea of when to use what speed, and then just program that in. So let's talk a little bit about memory a little bit more. You're probably all familiar with solid-state drives and hard drives. If you want to read something from there, it might take something like 50,000 clock cycles for your main memory, which is your RAM. you're going to have less of it, but it might take only 50 to 200 cycles. Then you have your L3 cache, which is on the chip, but not in the core. That's 30 to 50 cycles. Your L1 and your L2 cache are in the core. That takes far fewer cycles. And then your registers, as I mentioned with those instructions, only 1 to 2 cycles. So this is why it's important, if you're doing reading and writing operations, to lay out your data in a smart way, so that it's not constantly going to your main memory, or if it's using swap memory, then to the hard drive. You want to make sure that you're using what's in the cache to the greatest extent possible. So when you read and write data, you want to do it linearly. Even if you have these crazy classes or data structures or multi-dimensional arrays, at the end of the day, everything is stored in 1D vector format. It's just a string of ones and zeros. And so if what you're asking for, or if you're trying to read or write, and the spot is not in the cache, it will trigger a cache miss. And so this results in a fetch. It halts the pipeline. It slows everything down. So I mentioned there's this multi-stage pipeline, and that means that the processor, even as it's executing one thing, is preparing to execute many more things. So halting the pipeline is a very bad thing. The fetch, of course, returns much more than what you ask for. It's not just going to return one integer into your cache. It's going to get that plus some more after it, because it will anticipate that you need data around it as well. So what you want to do is linearize your read and write in order to utilize this most efficiently. And these large vector operations do benefit from prefetching. Prefetching is something that I have never been able to get to work manually. You can say, I will need this data in 400 cycles in the future, or whatever. And it always slows things down when I try and do it manually, but the processor does have the ability to do this, and the compiler does this as well. Something to remember is that random access is always going to be the worst. If you have a vector of data that can be sorted, it's better to do that so that you can access it linearly rather than access it randomly. So you want to use knowledge of your data or algorithm to restructure your data to access it more efficiently. You can't always do that. Sometimes there are limitations, but you want to hope that that's not the bottleneck in your code. So for instance, if we're looking at some 2D array, which I've written in 1D format here, you can either do column major access or row major access. So in this case, I've stored it in memory, first row, second row, third row, all at the same time. So if you access it the correct way, where you're doing the first one, the second one, the third one, the fourth one, etc., that would be this one down here. And if you do it the wrong way, then you're accessing the first spot, and then the nth spot, and then the 2nth spot, and you're skipping large portions. And so this will empty the cache. That's what we're looking for. And so you can see in this case, you get something like a 10 times speed up. And this will greatly depend on the size of your data and the data structures that you're using. So you want to make sure that you're doing this the right way. Most of the time you will, but keep it in mind. One more thing I want to talk about is branch prediction. So not all of you will know this, but branching is terrible in code. So these are if-else statements. So the modern instruction pipeline has 1 to 2 dozen stages, and the result is not known until a certain statement is executed generally. And so what do we do then if many, many operations are queued up behind it? Well, there's this branch prediction unit, which is fairly old now, but it was very revolutionary at the time when they put it in. And what this does is it stores probabilities for the branch outcome, and it will update it dynamically. So if you're going through some loop and you're trying to accumulate something or evaluate some statement, then as your code is running, it will update these tables and perhaps reorder your operations so that it's doing fewer jump statements and accessing the code more efficiently. So what I want to mention here is that if it guesses wrong, it will cause a 10 to 20 cycle delay, as well as a jump operation. And all of the instructions are flushed out of the pipeline, and it takes some time to get back to where you need to be. So there's a solution to this. Sometimes you're able to replace an if statement with a math operation. So for instance, if you want to conditionally add something, you can add 0 or the value that you want to add. So the idea is to do nothing, in some sense, if the statement is false. Here's a great example. So suppose you have some data here, and it takes values in the range of -1 to +1, and you want to only accumulate the positive entries, okay? One way to do that is to go through, check each one, see if it's positive, and accumulate it if so. However, you can change this into a math operation as well. And this crazy thing right here is going to be, it's going to evaluate to either -1 times the value, right here, x, or to 0, okay? So I'll break this down a little bit. What's happening here is you have your data value here, okay? This and thing here is taking the address of it, okay? It's casting it to an integer, and then it's dereferencing it. So what you have now is just the string of bits, okay? And then it's doing some bit arithmetic. This is a right shift operation by 31. And what you're doing here is you're looking for the sign bit, okay? The sign bit is the most significant bit. There's one bit that will tell you if it's positive or negative, and you're extracting that. And then you can do this negation operation here, so that this whole thing will be either all ones or all zeros, okay? If it's all ones, that's equal to -1, if it's a signed value. If it's 0, then it's 0. So what you're doing is you're doing -1 times this value or 0 times this value. And so you can see I've changed this from plus equals to minus equals. So there are variations on this. There are cases where it's applicable, cases where it's not applicable, but you should try and do this if you can. Like I mentioned, in GPUs, these types of things are useful.
Do you have to write that in one line? Like,
No.
When it makes sound, and you split that up a little bit?
Not at all, because the compiler is going to translate into, however many instructions it takes to do that. The point is, I kind of wanted to write it on one line just to show that those operations are equivalent. It looks terrible. It's not very readable. So in general, what I would do maybe is write a comment that says, that's what it's doing. Yeah, it looks terrible. This is the worst part of C, I think, is that kind of stuff. But it matters sometimes. Yes?
What is the name of this method if I wanted to look it up later?
Branch elimination. So yeah, the idea is, so let me tell you when it doesn't work. It doesn't work if you need to read or write conditionally. Then it won't work, because you're still accessing the memory, okay? If you're doing math operations or you're trying to extract some subset of your data, then it would work. So as another example here, you can see it offers about a 3 times speed up when I eliminate the branch. That might not seem like a lot, but 3 times speed up here, 2 times speed up there, you use all the tricks together, and it can make a difference. It's the difference between waiting 3 hours or 1 hour for your code to finish. So I want to just summarize what I've said so far before I move on to parallel programming. You don't need to be an expert in these things to write good code. A lot of it is going to be taking your code and looking at one particular point which you think might be the bottleneck and working really hard to make that part optimized. That might mean asking questions on Stack Overflow, or looking up how somebody else has done it, and that's perfectly fine, and that's how you learn. So the first version of your code should always be easy to read, easy to debug, and produce the correct solution. And then the second version, that's when you should start doing your tricks. You want to think about your data structures. Can you use float precision instead of double precision? Because that, again, you use half the amount of memory. Think about the cost of your instructions. I showed previously in the table, there's an operation that calculates sine and cosine at the same time, in roughly the same time as it takes to calculate one of them. So if you need both of those instructions, then you're able to take advantage of that. There are other operations like that as well. You want to think about, for instance, can you use Euclidean instead of spherical coordinates, right? If you're calculating distances, it's a lot cheaper to do a square root than it is to do arc cosine, for instance. You want to think about your memory access patterns, eliminate branches, and always benchmark, always.
Can I ask a question at this point?
Yes?
So, you showed us a number of tricks. So if I just run my compiler with -03, how much of this will the compiler be able to do on?
The compiler will take care of it with O3. So with these, I had to do O0, right?
Maybe the data layout can't reorder data.
Probably you're right about that one, yeah.
But like the branch elimination, it can probably figure that one out. So
Maybe. It depends also because in the example here, and all of the code is available for you to look at and compile and test, copy, paste, whatever. But it's important so I was going to say, in that example, there was an equal number of values between, on the positive side and negative side, right? So if there were only 5% of your values, right, that were actually being accumulated, it might change that. So that you want to sort of use your knowledge of your data in that case. I don't know how the compiler would perform, but we can modify and test it.
And have you ever spit out the assembly code and looked at it to see what exactly the compiler is actually doing?
I have. I'm not great at reading assembly. There's a lot of extra stuff happening. I don't know. I don't know about that. I wouldn't advise it unless you really have a good idea of which portion of the code you're looking at. Yeah. Okay. Any other questions about this portion before I move on? Yes.
Are there any good software tools like that to go through the benchmarking code? A lot of different timings and stuff like that.
I personally just use like a stopwatch for it, so it measures it to the microsecond, and I'll talk a little bit about how to benchmark code with that. You could also use the time command in Linux is one way to do it, but there's other stuff happening there as well that will. So if it's a very long operation, then the overhead doesn't matter. If you're trying to measure something that will only take a few microseconds, then it might be better to put something in the code yourself.
Other profilers?
Probably. I don't use a lot of them, but I would say you could use like Valgrind or, yeah, I'd probably recommend Valgrind for that. Okay. I want to talk a little bit about parallel programming now. So switching gears a little bit, still thinking about architecture, but in this case, we're thinking about how to do multiple tasks at the same time when we know that they are not blocking operations. They're independent operations. So the easiest place to start if you're working with C or C++ is going to be OpenMP. So OpenMP, as I've shown it here, it's a work sharing construct. It uses 2 or more cores on a computer. if the processor supports hyperthreading, then 2 OpenMP threads may execute on a single core. So hyperthreading is something which may or may not be enabled in a supercomputer, just for stability reasons. But what it means is that in many modern processors, there is sort of an extra little cache to have things ready to go for another thread so that you can do 2 threads per core. If you're using a Xeon Phi processor, it can do 4 threads per core, but not very many people have those. So you can see here you might have some parallel task. You have your master thread, which will become one of the threads that do the parallel tasks, and then it launches some other threads, and then it rejoins. And so something to think about is the amount of work that you're doing in that parallel task versus the overhead required to launch and rejoin the thread. So if the parallel task is very short, if your data is very small, it's not necessarily worth doing that. For compilation, you can compile with these flags and include just one header. As I mentioned, always benchmark your code. So let's look at another example. Suppose we want to add 2 vectors. So in this case, you can think of it as either an array or a C++ vector. Let's look at this. So you do this operation, z equals x plus y, and it takes some amount of time, not very long. To parallelize it, you just add this one single statement, along with the header and compiling it differently. But in terms of modifying the code, it's really minimal work. You do pragma, which is a preprocessor flag. OMP tells it that you're going to do something with OpenMP. Parallel means this section below it is going to be parallel. And for means the very next line is going to be a for loop. So what it's doing here is it's taking these statements and it's going to distribute them among however many cores you have. Now, I haven't specified how many cores or how many threads. In general, it will use all of them. Okay. So on this computer that I tested it on, I used 48 threads, and you can see that it took about 0.83 seconds instead of 3.27 seconds. You might be asking, why is it not 48 times faster, right? Or even close to that. And the answer is there's a lot of other stuff happening. You have to read memory and write memory. Those operations cannot go in parallel. There's a lot of overhead going on here. And that gets us to Amdahl's law, which says that only a certain portion of your code can be parallelized. So supposing you're not running the exact same thing on different cores, suppose you actually do launch other threads from your master thread, some portion of it will never be parallel. So if 5% of your code is serial, and that might be from I/O operations or some other operation that comes maybe before your parallel portion, you can only ever get a 20 times speed up, no matter how many cores you use. So what you want to do when you're benchmarking your code is test with different number of cores, and you'll find that you generate one of these curves. And you want to find out where you end up, and that will tell you your parallel efficiency. And we'll talk a little bit more about specifically how to measure that. So let's look at reduction operations. What if we want to use a counter? Okay, so let's have 2 vectors that contain random numbers, and we want to count in how many cases do the sum of them equal less than 1/2. So the problem here, if you didn't have this clause, is that you'd have multiple threads trying to access this variable at the same time. And that's a problem. Okay, first of all, it has to be in the L3 cache where multiple cores can look at it. And yet, for any single thread, it's going to have to pull it into the L1 cache and into the register and modify it and then put it back in the L3 cache. Of course, the problem is if 2 cores or 2 threads do this at the same time, they might have conflicting results. And so what you do is you add this flag called reduction. The operation is a plus here. There are a few different options you can have, but it's easy enough to look it up. There are lots of OpenMP tutorials, and you name the variable here. Now this has to be some simple, plain data type. It cannot be a class, it cannot be a struct, it cannot be an array. There are other ways to deal with those. But in this case, you tell it that multiple threads are going to be accessing this counter and incrementing it, and it will make sure that you don't have that conflict. So what you see here is a 24 times speed up because of that when you use 48 threads. So that's pretty good. Now, I want to talk about random numbers for a moment. In a lot of these examples, I have just filled the data that I've allocated with random data. But if you're using multiple threads, you have to keep in mind that most of the generators are not going to be thread safe. And what that means is if they all depend on a seed, they all depend on a starting point. If two threads have the same starting point, they will generate the exact same random numbers. So if you want to generate random numbers with 48 threads and try and get a 48 times speed up, then you want to make sure that they don't use the same seed. So what we do here is we break up the parallel statement and the for statement. So what this means is that you're going to declare that this portion within these brackets is going to be parallel. It'll be distributed among the number of threads. And then also this for loop is going to be distributed, but not in some nested fashion. So what you're doing is you're saying each thread is going to use this boost random number generator. It's going to do an XOR operation with whatever seed your master thread determined in order to ensure that you get a unique seed for each thread. So this is just a simple way to do it. And then you're able to do something in a for loop like this. So it's fairly straightforward if you know what to do. Any questions so far? Okay. So here we see a 21 times speed up. Pretty good. I should mention also, if once you get to testing these examples, you will notice that the random number generation takes a lot longer than the actual operations that I've shown. Random number generation, good random number generation, is an expensive operation, and so that's why it's something that's good to parallelize. So let's talk about, for instance, an adjacency matrix. So you might use this for some network system, but really it could be, any matrix operation that you're looking at that's symmetric. So one way that we can do this is to parallelize the outer or the inner loop. So you see I have a nested loop here. This statement is only going to apply to this line here. So each thread is still doing a for loop, okay? And importantly, you can see that it depends on this index here. So each thread is going to take a different amount of time. That's not good. You want your threads to be balanced so that they all end at the same time and your code is not blocked on one really long thread. So that's not the best way to do this. What you can do is remap things. So when you are looking at a for loop where you've designed it in this fashion so that you're going through I between 0 and some number, and j is above I. So this is some n log n operation. What you can do is you can remap your indices. So imagine at first you're just looking at the upper triangle of this matrix. So if this is a graph, you would say these are the connections in the graph. What you can do is remap this region B up to here so that then you have something rectangular and it's much easier to break down into a linear fashion. So what you can do is this. Turn a double for loop into a single for loop. You do some bit shift operations. What this is doing is making sure that only this region B is being, the indices there are being changed. These ones are not changed at all. And what we see is that with no parallelism, it takes about 3 seconds. If you do the naive parallelism with the double for loop, it'll take about 0.18 seconds. But then you use this trick here, and it takes slightly longer. Now, why does that happen? Well, this is why it's important to benchmark the code. The reason this happens is because the operation that we're doing is not super expensive, and the access is still fairly regular, so the compiler is able to optimize some of this. So this is a good example of where you want to make sure that you test your code. So, any questions about OpenMP so far? I want to emphasize that if you're writing code with OpenMP, there are many, many tutorials online. It's very easy to get started with, but these are just a few examples. So let's talk about these vector registers that I've been referencing. So if you look online, you'll see that there's this intrinsics guide put out by Intel. So these instructions are specific for the architecture, and they are using these vector registers. This is an older graphic, so it only has 128-bit here, but newer generations will have either 256 or 512-bit registers. And so these are called XMM, YMM, or ZMM, depending on the size of them. So to see if your processor can support it, you can execute this command here to see this file here will tell you all of the features of your CPU. And you want to see if it has this AVX or AVX2 or SSE. There are a ton of flags that you can look for. Compilation can be a little bit tricky for this because it's so hardware dependent. But as an example here, you can use these flags with G++ or GCC, and the -m tells it to go straight to the assembler, skip the compiler. And so it's telling the assembler to use AVX2 instructions, and it's telling the architecture and what to tune it to. And so there are different flags that you might use for different processors. So going back to this example, where we're looking at vectors, suppose we want to do an inner product. This is a very common operation in math and physics. So we could start with the vector multiplication before we accumulate. And what we can see here is that there are these crazy functions here that look very foreign, but it's really the same as using any other library. Okay, these are defined somewhere else. You can look them up online. And what's happening here, as I mentioned, you have to specifically tell it to move the data into those registers. So it starts out in the general purpose registers, and then you tell it with this load U, so that's load unaligned, meaning it's not necessarily on a certain boundary, and you give it the address of it. So because you cannot have a simple data type which takes 256 bits, you're going to give it the address of the starting point, and it will take from there the next 256 bits or so. You do this multiplication operation once the data is in there, and then the store operation will put it back into the general purpose registers where you can use it as you normally would in this Z vector here. Okay. So something I want to point out is this third line here is the most important one. You want to make sure that the time that this takes greatly exceeds the time that all of your loading and storing operations take. So that might mean redesigning your code a little bit so that you can do more things in these vector registers and you have less transfer back and forth.
So let's keep adding 4 doubles here at the same time?
Let's see. It's doing 4 longs.
4 longs.
So that's 2.
4
Yeah. So it's effectively, as I mentioned with the loop unrolling, you can think of it as doing the same thing where it's doing 4 at a time. So while you do have these instructions for loading and storing, this multiplication might still take the same as a regular multiplication, but you're doing 4 of them at once. Okay? So if there are many, many operations here, then it might be smart to use vectorization. And so you can see it goes from about 3.3 seconds to 2.7 seconds when you do an operation like this. So there's a little bit of a speed up, but it's very, very dependent on your application and what data types you're using and what else is happening in the code. So we also want to perform this reduction, and the reduction is just a fancy word for a sum over a vector of data. And so here you have this other operation. What you're going to do is you effectively have 256 bits, and you want to tell it every 64 bits. I'm going to consider it separately, and I'm going to do this add operation. So first of all, you do this set operation to make sure that the result is all zeros to start out with, because you're accumulating. You load the data in, you multiply it, you add it to get the sum, and all of that part's inside the for loop. At the very end, you're going to do your store operation to save the result. So your accumulator variable is in the vector register. It's not that you're putting it there, taking it back at every iteration in the for loop. And then you have your total at the very end. So here we can see it's a little more than twice as fast to do it this way. So an interesting point here is that adding this extra step did reduce the overall time. And this has to do with what's happening dynamically inside the processor, and the fact that the overhead is not as important as the operations like these ones, the multiplication and the addition, once you're doing more of those operations. So finally, we can add OpenMP to this, do that together. And it's as simple as this. You add your OpenMP parallel statement. So this is your for loop. You'll notice that I have this plus equals 4 now, because each operation is taking care of 4 pieces of data. And then there's also this critical statement. And critical means that it's similar to the reduction, but in this case, you're not using some simple data type. You're using this M256D data type, which is just a 256-bit struct, effectively. And this makes sure that only one thread at a time can perform this operation, so that when you're accumulating something in your sum variable, 2 threads are not going to write to it at the same time. And so we can see we go from 4.34 seconds to 2.09 seconds, and then we get a little bit better, 1.99 seconds. So the small difference can be explained by Amdahl's law, and it indicates that we're close to the theoretical maximum speedup. So you saw those curves that sort of asymptote up to whatever the maximum will be. So if you're adding more threads, then it's not going to necessarily get much better if you're close to the theoretical maximum. So I think I might skip MPI, but you're welcome to look at it later. I want to get to the tutorial portion. MPI is something that you probably wouldn't use unless you've exhausted all of your other options. The basic idea is you have multiple computers this time working together. So on each computer, you might split up your tasks among the cores, and then you might have multiple computers that are working in tandem. But of course, the problem is there is a very long latency in transferring data from one computer to another. It's much longer than transferring data from level 1 cache to level 3 cache or something like that. So there's lots of examples that you can go through. Let's look at the summary of what I've talked about. Usually you start with OpenMP because it's the easiest to write. I've shown this in many examples. You want to try and convert all of your loops into single for loops. So of course, for loops are the obvious place to parallelize. Longer tasks are going to provide a better speed up. you want to play around with these clauses that I introduced. There's the schedule clause, which tells it how to break it up. Are you going to have each thread do one thing at a time and then ask for more work, or is it going to do maybe 10 iterations of the for loop and then ask for more work? You want to use vectorization, SSE, AVX, whenever you're doing numerical operations with vectors or matrices. Okay, so lots of linear algebra computations that I'll talk about this afternoon are going to be doing this. The compiler is going to know to use this. So you want to start out with OpenMP, make sure you're using the correct data types, use only half of the maximum number of OpenMP threads, so no hyperthreading. That's in general a good rule. And then MPI comes last, and it can be more difficult to write, and you want to make sure it's balanced between all of the computers. So, any questions so far?
Here you said that you need to use half the maximum number of open threads, so would the number of threads be equal to just the number of cores?
No, and that's something, it depends on the computer. So this is something where you might want to look at the CPU info file to see if hyperthreading is enabled. It's not enabled on all machines. So in some cases, for instance, I showed 48 threads, but there were only 24 physical cores. So you might still get some speed up, but it might block other things as well. So for sure you can do the number of physical cores, and then you want to test to see if beyond that you're getting any speed up or if it's just blocking it and causing things to slow down.
I've actually run into a situation where using less than the number of physical cores was better because it was two CPUs connected on a bus. That was the node. The node was like two CPUs in the bus. So it said, oh yeah, this is 28 cores, but it was really 14 cores plus 14 cores.
Right.
And the traffic on the bus between the two 14 cores just killed it. So you're
Yeah.
up running 14 threads.
So this is why, again, the operations that you're doing will matter. And in many cases, when you see something like 28 cores on a computing cluster, it might be because there are actually two 14-core processors on the same motherboard. That's something to think about. The bus bandwidth is limited. So yeah, that's interesting. I didn't think about that. Okay, any more questions so far? Okay. So for the tutorial, it's sort of going to be a little bit self-guided, but I'll also be able to help. What we're going to talk about is random geometric graphs. And for those who are interested, information routing through these random geometric graphs. So in the Riemannian case, one thing that has been shown is that if you look at the internet at the autonomous system level, so these are data centers, then you can embed it into the Poincaré disk. Okay? So this is 2D hyperbolic space. And those at the center are essentially the hubs. They're very well connected. And those further out are going to be something that is more remote or regional. And then in terms of angular organization, we see that it's somewhat geographical. Okay? So the reason this model is important is because if you're trying to route information from one place to another, and you have this network structure that's embedded in here, then you can simply follow a geodesic. You do not need the BGP routing tables. And this is important because a few years ago, those BGP tables overflowed. There were no more spaces for entries, and so they had to increase the size. So this is perhaps a model for the future internet. So on the right-hand side, you can see essentially the same thing, but instead of talking about the internet, we're talking about space-time now. And the radial coordinate is the time, and the angular coordinate is the space, so it's a 2D model. And what we're looking at here are causal connections. So it's very similar. In both cases, you're looking at points embedded into some 2D space, and you have some rule for whether or not they're connected. We're going to focus on something a little simpler, though.
What do the
So in this case, the dots would represent quanta of spacetime, atoms of spacetime. And then the connections represent causality. And so in this model, you're able to say all of the geometric and dynamic information is encoded just in the graph structure and the graph growth rules. So this is one of the approaches to quantum gravity. Yeah, and here I've drawn the light cones in this case. So this would be for de Sitter in 2D mapped to the Poincare disk. So the general layout of what I want to do is first we're going to think about what data structures we want to model these graphs. Then we're going to construct them. Then we're going to perhaps measure some simple structural properties. And then as a challenge, route information packets. So just to start out, you should check your email for SSH keys. Everybody should have one. And then see if you can SSH to Google Cloud all at once. We'll see if it works. So the way that I've designed this tutorial, you can start out doing some of the simpler tasks and then perhaps move on to the more advanced ones. There's a solution in this file, tutorial.cpp. So if you get stuck, you can check that, but I wouldn't advise to just go to that immediately. And then in the slides here, there's more rules on what to do. Let's see. So first, see if you can connect. You don't, it should be in your email? No?
Yeah, I got an email. There's a Peter. Some past students.
Yeah.
Password. Did you get the email? Oh, there was an email. Okay.
Okay, who did not get an email? 1,
Yeah.
3, 4. 5. Ah, it's the RPI students.
Yeah.
Okay.
So you have access to the Dropbox folder?
Yeah.
There's a participant spreadsheet here.
Yeah, I sent it to them.
And there's a separate tab for RPI students.
Yeah, I know. They must have set it up with just. So if you don't have an SSH key, then maybe share it with somebody else. You'll be using the same resources, but in terms of reading and writing, you can just copy the directory, for instance. Time to get started. So this afternoon we're going to be talking about computational methods for linear algebra. It might seem like a little bit of a dry subject, but it turns out that almost every problem in physics or computational physics ends up using linear algebra one way or another. So what I'm going to try and do is motivate this with some examples. So to start out, again, the main points that I want you to take away. As I mentioned, linear algebra is ubiquitous in scientific computing. When faced with a problem, though, we have many different ways to solve it. There are many packages, many devices that you can use, many methods. So it's not always obvious where to start. So I'll give you some starting points and some example code that you can use, hopefully, in research or classes later on. I want to emphasize that all of machine learning and artificial intelligence relies on fast, low precision linear algebra. So this is matrix and vector algebra. right here. And the best, meaning fastest, solutions are those which are hardware dependent. And because of that, Google, NVIDIA, IBM, Intel, all these other companies are investing heavily in hardware for this. So if you've heard of tensor processing units, similar to graphical processing units, this is sort of the new hardware that's being designed to solve these problems in the best way possible. So what we're going to do this time is we're going to start out by looking at some basic linear algebra problems with LePac and BLAS. These are some older implementations that you might be familiar with, but before we get to the newer stuff, it's important to review the older stuff because you'll sort of understand what everything else is based on. And then for physical examples, we'll look at some SON transformations, which are effectively rotations. We'll look at page rank and spectral gap problems. We'll look at spectral graph theory for discrete geometry, do some deep learning with backpropagation. We'll look at this in the tutorial a little bit, and also maybe a little bit of principal component analysis. So to start out, BLAS and LePac are some of the oldest linear algebra implementations that are still around. So they were released in 1992 in Fortran 77, and ultimately so they replaced what was called LinPac, which was used in the 1970s. So these methods have been important for a very long time. For these particular packages, there are bindings for C and C++, Python, Julia, R, Mathematica, MATLAB, MKL, CUDA, OpenCL. Just about everything you can think of is somehow related back to this. There is support for all sorts of data types, dense matrices, packed, banded, sparse matrices. I'll talk a little bit about what that means in a moment. The most important thing to know is that there is a standardized function naming scheme for this. So if you're looking for how to do a particular operation, one way that you would do it is you would look up on the netlib website a particular operation that you want to do or function, and it will tell you exactly how to do it, what all the parameters mean, how to implement it. But just in case that is difficult or confusing, I've also provided lots of examples. So what it's based on is you specify the precision, so you can do single or double precision in either real or complex numbers. You specify the matrix format, so there's general matrix format, which means it's not really going to take advantage of much symmetry or anything. You can look at symmetric real matrices, Hermitian matrices, banded matrices, all sorts of different things. There's dozens of these, so it's not worth memorizing at all. And then finally, the algorithm is going to be either somewhere between 1 and 3 or 4 characters. And this describes what it's doing. Is it solving a linear system? Is it doing matrix vector multiplication, singular value decomposition, eigenvalue solutions, any of that stuff. So let's get right into the examples. Consider the following. You want to do a matrix vector multiplication with some general matrix. And so here we have this function. So it says you're doing single precision for a general matrix, and you're doing matrix vector multiplication. So that's the basic idea of what's happening there. You're specifying a floating point matrix in column major order. It's important that it's stored in column major order. So as I mentioned previously, all 2D data is actually stored in 1D, just a sequence of values. In this case, it's column major, so you do the first entry, the one below it, the one below that, for full column, and then you move on to the second one, and then the third one, etc. So what you're actually doing here is you're calling a Fortran function, and even though it's not declared anywhere, you don't include any headers, what you're doing is you're calling a function that you link against in a library. So when you compile it, you use this -l BLAS, and it will find the BLAS library on your system.
Can I make one comment?
Yes?
That underscore after the SGENV some compilers want the underscore and some compilers don't want the underscore.
That's correct. So what I've written here is for G++. If you're using GCC, it will be slightly different, right? So you wouldn't have extern C, you would just have extern, and you wouldn't necessarily have that underscore. So it does depend on that. I chose to do it for C++ because it sort of covers everything and gives you the opportunity to use other C++ stuff if you need it. So it'll make more sense once you go through the code, actually. Everything is passed as pointers. So you can see here, when I call the actual function, I'm using this ampersand. And so what that means is it's taking the address of that variable. It's not passing the variable itself. And the reason is because you're sending it to a function in another language, and what that function will be looking for is something in memory. Of course, for something that's already an array, just passing it like that will send the address of it. Okay. So what you see here, you see some other stuff that I've defined. And these are just other variables that are part of the function. And basically what you do is you look up the function and it explains what you want to put for those. So here I put, for instance, for the transpose variable, I say n, meaning don't transpose A, whereas if you put something else here, then you would be able to do the transpose of A instead, and it would just take care of that. Yeah, so pretty straightforward. So if we look at, instead, complex variables, this is something that when I was first learning it was not immediately obvious to me. When you're working with complex numbers, this isn't a standard data type necessarily. I mean, it is a standard data type, but it's not something that you work with all the time. In C++, you're even using this template variable. So how the heck does that interact with Fortran? Well, what you're going to do is declare it just like this. And this I variable, capital I, is reserved. You cannot use that for other variables if you have included the complex. I haven't written it here, but it's in the code. If you include complex.h, then that will be used to indicate the imaginary unit. For the function prototypes, you're going to use void star. So that just means that you're passing it some generic memory segment. You want to keep in mind that complex math uses twice the amount of memory because you have a real part and a complex part for everything. Furthermore, complex math is more expensive than regular math. You're doing, just to multiply or divide complex numbers, you're doing a lot of extra operations on the actual real and imaginary parts behind the scenes. So even if that's implemented directly, and you can just write, A times B, and they're both complex, there's actually a lot of other stuff happening behind the scenes. So that's sort of why I wanted to emphasize the instructions earlier and how they're not all created equally. So moving on to matrix-matrix multiplication, let's consider this function. So what we're doing is complex, C, Hermitian, matrix-matrix. Fairly straightforward. In this case, we have 3 matrices, and we're storing the result in the third one. One of the things that you have the opportunity to do is change the order of these. So for instance, this side variable says A is going to be on the left side. A is my Hermitian matrix. B and C don't necessarily have to be Hermitian. I put the actual URL here in case you want to check out all of the functions. Each of them has a page explaining what values to use, some source code for what's actually happening behind the scenes, in case you want to write your own implementations or see if you can do it better. I would suggest doing that for a few of them. It's very useful to understand how these things work, especially for some of the more advanced stuff. Something to point out, these functions are not multi-threaded. Okay, so even in the cases where you can, where you have independent operations happening, like If you're doing matrix-matrix multiplication, obviously you can have rows and columns multiply independent from each other, but that's not happening here. So that's something that some of the newer packages will take advantage of. Yes?
What would the time complexity be for this matrix multiplication? Would it be like if you're doing brute force, it would be n squared, right?
I think it's n cubed.
N cubed?
Yeah.
Yeah, so would this do any better?
So I think it's still n cubed. The time when you would be able to beat n cubed, I think maybe the best is like n to the 2.7 or something like that, for the best implementation of matrix-matrix. But I don't think that's done here.
Yeah,
Yes.
but one thing is that if you look inside of laws of compact, they've done cache blocking and things like that. So it's not the number of operations is different, it's how it does with caches. So they're much faster than what would happen if you wrote it yourself.
Yeah, so that's another reason why it's good to go look at the source code, because you can learn some tricks from there as well. It does start to change things around if you're using sparse matrices, if you're using banded matrices, things with certain symmetries that you can take advantage of. Then you might be able to beat that complexity. So if we look at sort of a simple example for linear systems, suppose we want to find the current in a circuit, large circuit with resistors. It's a very basic physics 2 example. Using Kirchhoff's and Ohm's laws, we see that we have a linear system where we're just using V equals IR pretty much. And we can look at each of these individually, basically every circuit that you have, and write it out so that we have a matrix of resistors and solve a linear system that way. And it's a lot easier than doing it out by hand. So to solve the classical linear system, AX equals B, so in this case, RI equals V, you would use this method here. So I've used complex double, not because it's needed here, but because it's sort of a more complicated version that, it's slightly less intuitive, but here's the example anyways. So what you're doing is you're working with an n by n matrix. You can specify multiple columns for x and b. And so that's not something that you're necessarily used to in linear algebra. What that means is you're using this matrix A to solve multiple linear systems at once. You don't have to do that. For the example I just showed, you wouldn't need to do that. But you have the ability to do that. So what you're doing is you declare some workspace variables, and the size of this is going to be dictated by what's in that documentation that I showed you. So you go to the netlib web page, you look up this function, or you Google, I want to do solve a linear system with LPACK, and it will direct you over here. And once again, you declare all of these extra variables. You write this function out, again with the underscore. You pass all of these variables, most of which are not super important to understand, but they're workspace variables. And in this case, you need to make sure that it actually succeeded, because depending on what you put in there, if A happens to be singular, it will not necessarily converge. So you have this info variable, which is essentially what's returned. So when you call a Fortran function, it does not return a value in the same way that you might get returned from a C function or a Python function. You have to pass it something that it stores the result in there, and then you read it afterwards. And then based on what that return code is, it will tell you whether it succeeded, or if something went wrong, what did go wrong. So if there are a few methods that it tries. It tries an iterative method. If that fails, then it will do an LU decomposition of A, and that's basically where it decomposes it into an upper and lower triangular matrix, and it just stores that in A instead. So it's important to know that you might be overwriting your data as well. And in this case, when you compile it, you need to add this extra library here for LPACK. And you need to do them in this order. That's important.
Do they, I've seen when compiling Webpack and Fortran before, you need an extra like dash, capital L, and like to point where it had, do you ever need to do that in C or C++, or is that just?
Yes. So what is happening there, when you call something like GCC or G++, there, and it's going to look for certain headers, certain libraries, it has a predefined list of places that it looks. And it's in certain environment variables. So your headers are going to be in the cpath environment variable. Write it down. So cpath. So if you add a directory to that, and this is something that's easy to look up on Stack Exchange or something, if you add a directory to that, then it will look there as well. So it automatically looks in something like USR, USR/local, all of the regular system places. But if you install something, an add-on package, you would need to do that. Or you can do, when you compile it, if it's not in here, you can do dash capital L and write the path there, and then it's effectively like adding it on to that.
So you can modify your cpath to just include that?
Well, so cpath is for headers, and then you have library path, and also LD, library path. And those are the three ones that you really want to pay attention to. If it can't find something, it'll tell you can't find the library. You'll know immediately that that's why. It's because it's not looking in the right place, supposing it's on the system. And then the other point to mention, I don't know if you learned this previously, but when I write something like -lblas, it's going to look in the directories for a static library called libblas.a. It's looking for that file. So the lib part is just replaced by an L, lowercase l.
What's the .a?
It just means static library. So if you see .a, it's static library. If you see .so, it's dynamic library. But in general, I've never had to use dynamic libraries for any of this. Yeah. So I want to talk a little bit about matrix factoring now. This is something that is sort of the next level up from these basic matrix operations. One of the things that you might have to do, for instance, is decompose a matrix. There are many reasons you would want to do this. So for instance, the LU decomposition, as I mentioned, you're taking some matrix A, and you're turning it into a lower and an upper triangular portion. And these can be stored in the same matrix A because they don't overlap except on the diagonal. And in that case, we know that for one of them, it will be all ones, so it doesn't matter anyways. So there are different properties that your matrices have to do these decompositions. This is where all that stuff you learned in linear algebra about positive definite matrices, positive semi-definite matrices, how that corresponds to what your eigenvalues will be. This is where you have to pay attention to that. And I'm not going to say that you have to memorize it. It's all on Wikipedia even. But it'll determine which factorization you want to do. And so for instance, if you're trying to decompose your matrix and it happens to be Hermitian, then you would use this Cholesky decomposition because it's about twice as fast when it's applicable. So it's worth knowing the differences between these. There are all sorts of variants, of course. What this really means is that you want to keep these basic ones in mind, and then for your particular problem, you will look up the properties of it. Say my matrix is symmetric, or my matrix has all positive eigenvalues because maybe they correspond to probabilities or something. And then that will indicate which method you should look at. There's also QR decomposition. In this case, it's decomposing it into an upper triangular and an orthogonal matrix, or if A is complex, then it will be unitary. So this would be useful, for instance, if you want to know the absolute value of the determinant. Okay? There are certain problems where that would be useful. There's polar decomposition as well. It's really useful in materials engineering for stress tensors, as well as for computer graphics. It's good for that. And of course, there's the most well-known spectral decomposition, which is where you take a matrix and you decompose it into eigenvalues and eigenvectors. And that is important because it tells you many fundamental properties of your system. Related to that, we'll talk a little bit about it in a bit, is the singular value decomposition. And the basic idea there is you're looking at the eigenvalues and eigenvectors of the square of your matrix. So the important property there is it will give you all positive singular values. Yeah, as I mentioned here, there are lots of others. But what the most modern packages will focus on is what symmetries do you have, and it will use different methods based on the numerical stability and the speed of the algorithm. So really you're looking at just small tweaks of these ones. So let's look at a specific example that was actually used in the linear solution in one of the previous examples. So consider the LU decomposition of a dense matrix. So what we're looking at here is actually the PLU decomposition in LePac. And what that means is that it's using partial pivoting. So partial pivoting means it can exchange the rows, or equivalently the columns, in order to speed up the convergence of this algorithm. It's important to note that you don't need to have a square matrix to do this. You can do it with a rectangular matrix. Very simple to do this operation. You don't have very many other variables. You just have this pivot vector, which will tell you which rows were exchanged with each other. It occurs in place, meaning you don't need to have extra memory. So if you have a very large matrix, this is good because you don't need to have extra memory available for your result. As I mentioned, the unit diagonal elements of L are not stored. So along the diagonal, you're going to have the diagonal of the upper triangular matrix. And it's typically used as a part of many, many other LePac functions. So going back to singular value decomposition, it's a generalization of the eigen decomposition, or spectral decomposition, to general m by n matrices. It doesn't need to be square. It doesn't need to be positive definite anymore. So what this means is that when you decompose it, it's slightly different. So even if this is a square matrix, the singular values could be different from the eigenvalues in the case that it's not positive definite. So one way to think about this, you have the left singular vectors and the right singular vectors. And what you have, if you can see it, is you have m star m or m star. So this is the square of this matrix. So the left singular vectors will be the eigenvectors of one of those, and the right singular vectors will be the eigenvectors of the other one. That's all. And then the singular values are going to be the eigenvalues of that product. It's important for physics in particular, not only because they form an orthogonal basis, the vectors, but they represent symmetries of your system, okay? And the singular values are indicating the relative importance of such symmetries. So one of the things that you use this decomposition for is approximating data. If you have very, very high dimensional data, perhaps a very large matrix, and you want to extract a very coarse feature, you don't necessarily need all of the data. You maybe want to approximate it using some subset of the data. And so this is called either dimensional reduction or principal component analysis. And so we'll look at this in the tutorial a little bit. It's also used for computer vision in the sense that you want to look at an image perhaps and determine is this a cat or a dog, but not necessarily is it a brown cat or is it a Siamese cat. Maybe that doesn't matter. So looking at a specific example, again, we use this SGE-SVD function. So you're doing single precision, general matrix, singular value decomposition. And what you're storing here is your original matrix, some space for your left eigenvectors, some space for the transpose of the right eigenvectors. So it will give you the transpose of this upon output. You'll have a vector of singular values, and then some workspace variables. And you have the option to run this without actually calculating the vectors as well. So in the case that you only need the values, then it's a little bit faster to do that. So moving right along to some modern linear algebra packages. I'm just going to go over two. There are many others. These happen to be ones that I've used or like to use. But if you have others that you prefer, then you can use those as well. So, as I mentioned, BLAS and LPACK have been improved since they were released. So here's some examples. Eigen is a C++ header-only template library. It's extremely easy to use. There are objects or operators defined such as matrix operations. So if you have two variables that are matrices, you just use a little multiplication sign and it takes care of everything. And you don't have to worry about accessing elements or any of that nonsense. There's some parallelization for matrix math, but this is still under development. There's support for sparse data structures as well. Overall, I really like it. I think it's easy to use, and I think you'll see that in the examples. MKL is the math kernel library provided by Intel. It's free, but there's sort of a soft license. So you do have to go through Intel's website and say that you're downloading it for academic use only, and then you get a free copy of their compilers and the library and all sorts of other stuff.
Does the MKL only work with Intel's compiler, like the iFork?
No. No. So some of the examples, yeah, that's right. Some of the examples will have instructions for how to use MKL with something like G++. I've also included in the make file the line that you would use if you're using Intel's compiler as well. And you can see that I mentioned it here, using MKL or any of the Intel stuff is very difficult in the sense that you need a lot of flags to compile it. However, they have this advisor page, I think it's called the linker advisor, and you go through a series of drop-down boxes and say, these are all the specifications of my system, and it'll tell you exactly what to put. So it's a little bit extra work. It looks terrible, but it's not so hard in the end if you get it to work. One good thing about MKL is it includes much more than linear algebra. There are nonlinear optimization solvers, stuff for differential equations, as well as all of the eigendecomposition and all of the LPACK and BLAS is built into it as well. And for this, there are interfaces just for C, C++, Fortran, and Python. So if you want to use Python, it should be fairly straightforward. Yes?
So you mentioned a couple different libraries that people use for linear algebra. Is it necessary to have all of them, or can you just kind of like pick and choose?
No, it's not necessary to use all of them. I ended up at these sort of just because for my particular problem, I had very large data that I was trying to work with, and I wasn't sure what the best solution would be, what the fastest solution would be, and so I tried a couple different things. As with all of them, you see what works for you and what you're comfortable programming in. Some of them will be faster than others for specific problems. And so this is something where you would do a little research online to figure out what other people recommend or how other people have gotten it to work. It seems to be the rule with all of this. Okay. And of course, I should mention that it's optimized for Intel processors. So it will take advantage of all of these little registers and caches that only Intel knows about. So let's get right into an example using eigen. If you're doing a geometric rotation, suppose you have a 3D vector and you want to rotate it about some axis by some angle. It's very straightforward. It's a template header-only library, so you don't have to worry about linking against any libraries. You just include these guys up here. You declare some matrices, some vectors. So here 3f indicates it's 3 dimensions, and f is for floating point precision. So if it's more than 3 entries, then you might use xf or xd for double precision. You declare an angle. For initialization, it's super easy. You use this double chevron here, and it just puts it right in. And then you can do things like normalize function, and it will normalize your vector for you. For rotating about the z-axis, for instance, it's as simple as this. You just declare this function here, and then you do your matrix. This gives you a matrix out, and you do your matrix vector multiplication, and there's the result right there. So in terms of programming, it's much more high level than using Webpack or Blast. You don't have to worry about all of those workspace variables. So under the hood, it's still doing all of that stuff, but you don't have to worry about it as the programmer. And then I show here how to do it about some random axis, if you choose to do it that way. As I mentioned when you asked, if you can't find the headers, you need to add that to the variable cpath. So that's something that you might find you need to do for the eigen in particular. So this is not something that comes on most systems, but it's very easy to install. It is on most supercomputers, though, because it's fairly well used. So now for PageRank and spectral gap methods, these are 2 problems which are sort of dual to each other, so I chose to include them together on the same page here. For the PageRank, this is something that was developed by the founders of Google probably 20 years ago. And the idea is if you have a network of web pages connected via hyperlinks, how do you tell which ones are the most important? You want some way of ranking nodes in a network by importance. One way to measure importance is how often a page is linked to by other pages, okay? So rather than have, you can have your own private website and link to every single page on the internet, but that doesn't make you important. It makes you important if everybody else decides to link to your page, like as if it's, Wikipedia or something. So the physics problem that it corresponds to is a random walker surfing the web, clicking links, and sometimes entering URLs. So some fraction of the time you're just clicking links, going around, and then you can sort of teleport or do like a long jump by entering a URL and ending up somewhere else. So it's a random walk problem. And what you're interested in is the stationary state of the random walk. After an infinite amount of time, which pages do you end up on the most? And this is called either the PageRank or the eigenvector centrality. Now, it just so happens to be described by the largest eigenvector of your system. So if you're able, what I mean by largest is the one that corresponds to the largest eigenvalue. Okay. So if you're able to determine just that, you don't need to do anything, any matrix decomposition that might be more expensive. You only need one of them. On the other hand, if you're looking at the spectral gap, that is sort of the opposite end where you're looking at the smallest eigenvalue, okay? And in physics, this has applications everywhere. It's the energy gap between the ground and first excited state, or equivalently in a system where you have one or more eigenvalues that are 0, it would be the first non-zero eigenvalue. So in physics or solid state physics, this would be if you have a matrix that represents a Hamiltonian for a system and you want to know what is the energy gap, then you would look at the spectral gap. It's a particularly interesting problem recently because it was determined that the existence of a spectral gap is undecidable. What that means is it's impossible to determine whether or not it exists at a macroscopic scale, even if you have complete knowledge of the microscopic system. If you have a complete quantum description of your system, you don't know whether there will be a macroscopic spectral gap. So in terms of linear algebra, what that means is for your system, you're working with a finite matrix or a finite lattice. As you make that lattice bigger and take the continuum limit, eventually some spectral gap might pop out of it. but there's no way of knowing when that will happen or if it will happen. And then finally, the reason that this is a dual problem, of course, is because the smallest eigenvalue of one matrix is the inverse of the largest eigenvalue of another matrix. So solving these, you pretty much use the exact same methods, aside from a matrix inversion. So to do this, if your matrix happens to be large and sparse, meaning you have a large system, and sparse might mean that you have only local interactions, you wouldn't have non-local interactions, you can use the power iteration method. So in terms of pseudocode, what this means is you're just applying your matrix to a random vector over and over and over and over, and eventually you will end up with the dominant eigenvalue and eigenvector pair. So in terms of coding, it's fairly straightforward. You start with a random unit vector. You find your approximate eigenvalue this way. Or equivalently, if you're looking at the inverse problem, you will use the inverse of A, as I mentioned down here. You calculate your error, and you continue this until your error is sufficiently small. So you might pick some value for epsilon and say, once it's below this value, then it's converged. Yes?
This seems like a general method that would be applicable to any matrix. Why should it be sparse?
It should be sparse because of these matrix operations. They will be very fast and converge fast if you're not doing many operations, right? Sure, you can do it with a dense matrix, but it might be more efficient to use another method. Yeah, good. This will give you the largest eigenvalue. Yes. So it'll converge. There's a proof of convergence that as you multiply some random vector by A over and over and over and over again, the eigenvalue that you calculate on the second line here will converge to the largest eigenvalue. So if you're looking for the spectral gap, use the inverse power method, just replace A by A inverse. So the examples in the code will show you how to do this. Like right here. So in this case, we use the conjugate gradient method to invert a symmetric positive definite matrix. There are different ways to invert matrices in linear algebra. You would use the conjugate gradient method in this case because it's symmetric. There's also biconjugate gradient in case it's not symmetric. I would say use whatever symmetries you can to speed it up, but also try different methods to see which one's faster. So it's really not too much code to do quite a complex operation. What you're doing is you're declaring your sparse matrix here, so this variable m, and you will feed it with some data, which I'm not showing here, but it's in the code examples. You declare your conjugate gradient solver here with some template variables explaining how it's set up. But this is something that is even in the tutorial for Eigen. It has a very nice web page online explaining how to do all of this. You do some preconditioning with this compute function, and then you do your iteration over and over. So what I've done here is I've said continue until your tolerance is good enough or until you do some maximum number of iterations. And it's good to do this just in case it doesn't converge, right? You wouldn't want it to continue forever. In general, this can be kind of slow because you're doing, each time you do this solve function, you're inverting your matrix. So that part will take some time. If you are doing just the regular power method without inversion, then it will go a lot faster. And then you would maybe add some print statement at the very end to see what your tolerance is. It's always good to add print statements for something like this because you can get an idea of how far along you are if it's taking several days. So in the code example, there's this as well as the biconjugate gradient stabilized method. So in the case that you're doing spectral decomposition, here's a good example of why you would want that. If you want to know the number of K cycles in a random geometric graph, like we were looking at in the previous tutorial, this is a very relevant problem for discrete geometry. You want to know, for instance, as your graph size grows, how does the number of triangles increase? How does the number of squares increase? The number of pentagons? All of these features. Based on different symmetries of your system, some of them might grow, some of them might shrink, some of them might disappear entirely. And this will tell you how discrete spaces converge into continuum spaces. So here you're looking at your matrix. It's double precision. You have your eigensolver. And as soon as you call the constructor, it's solving the matrix. That's the step right there. That's it. Then you ask for your eigenvalues, you ask for your eigenvectors, and it's over. So it's a lot easier than a lot of other methods, and it's still very efficient, especially compared to something like MATLAB or Mathematica, because it's in C, it's compiled, and it will be hardware dependent. So when you compile something, the compiler is also looking at what specific processor and other stuff you have, and then reorganizing stuff to take advantage of that. So here I'm looking at the number of 3 cycles. And what I'm doing is counting, I'm accumulating the kth power, here the cube, of all of the eigenvalues. So I'm just doing an eigenvalue decomposition, taking the cube of each one and summing it up. And this just so happens to give me an integer. So for instance, in geometric graphs in particular, this is very important because the number of triangles is related to a property called the clustering, and the clustering will tell you if you have a geometric space or if you don't have a geometric space. It's a very important observable. And this is what you might get. Okay? So you see you have a very uneven distribution in terms of positive to negative. It's interesting that not all of them are positive, so we don't have a positive definite matrix, even though it's just some structural object. And we have many, many, many small negative eigenvalues. So that indicates that we might be able to extract some coarse features if we did something like a singular value decomposition. So on the other hand, if you're using MKL, it's a lot closer to going back to LePac, okay? First of all, you need to use these variables, MKL integer, and this will essentially either be 32-bit or 64-bit integer, depending on what compiler flags you use. But you must use that. You cannot use interlong. And I really want to emphasize that because when I was writing this example, I did use that, and I thought I could just cast it to an integer or cast it to an MKL int at the end, and it blows up in your face and says segfault. So please don't make that mistake. You use this MKL calloc to allocate in 0 memory. What this does is it aligns it, in this case, on 64-bit segments. So this is sort of an optimal way to make sure that your cache will be filled. Then you use their Feast eigensolver. So this was actually developed by a group at UMass Amherst, and it was good enough to get into Intel's math kernel library. And so right now they have version 2 inside MKL. There's also version 3 online if you end up needing to do something like non-symmetric matrices or any sorts of more complicated things. So you can see that you call this function here, you're using single precision, you're calling the Feast solver symmetric eigenvalue solver. And you add all these things in, again, you're passing the pointer to the memory, and I'm pretty sure, again, here it's because it's calling a Fortran function. I want to emphasize compilation is not nearly as easy as for the other stuff. You can look at the make file in the tutorial and you will see this. Something important about this, rather than just returning all of the eigenvalues, what you're telling it to do is look for some number of eigenvalues in a range, Emin to Emax. And then it will tell you how many it actually found. Okay, so it's a little bit different. So again, depending on your problem, that might be the appropriate thing to do if you only want to look in a certain range. For instance, if you only want positive eigenvalues, you might tell it to look between 0 and some really large number. I should mention also there's this FPM variable here, which is a 128 sized integer array. And that's basically just a bunch of flags that tell it whether it should do print statements, whether it should use this method, whether it should use this much workspace, use this iteration, whatever else. Something you look up and there's a big long table and it tells you all the options and you play around with it. So now I want to talk a little bit about deep learning since that's sort of what's going on with linear algebra today. To start out, so all of deep learning is based on linear algebra and effectively figuring out the coefficients of some polynomial function which approximates whatever you're doing. So a deep neural network consists of input layers, or input neurons, several hidden layers, and then an output layer. You have, for each neuron, some activation bias. So this is why it's called neural, is because it's based on sort of neurons in the brain. So you have an activation bias. You have a weight matrix, which says how much each one is connected to the other. And then you have this feed-forward back propagation, back and forth going on. And what this has to do with is how you update the weights and biases in your system so that it learns. So a learning step would be feeding forward. You're effectively initializing this to some random weight and bias, seeing how it performs with your data. It'll do terribly. And then you use a gradient descent method effectively to update these weights and biases. And the reason that we have multiple layers is because the features in the data are learned hierarchically. So it's going to first learn the very fine features, and then it will start to learn coarser features, even coarser features. So if you want to, for instance, have a classifier that says cat or dog, or some classifier that says letters of the alphabet, if you're trying to learn text from an image, then this is something that would be good for it. So this is what it might look like. Okay. And it's all based on this universal approximation theorem, which says that a feed-forward neural network with at least one hidden layer can approximate any continuous function on a compact subset of RD. So, like I said, effectively what you're doing is you have a big, long polynomial with unknown coefficients, and it will approximate some function that you want. And it's really as simple as that. Yes?
So each one of these layers, are they like matrices or like basis sets? What is...
So yes, they are neurons which have weights and biases associated with them. So in terms of linear algebra, the bias would be a vector and the weight would be a matrix. And so going back here, each of these is like the neuron, and it will have a bias associated with it, so some vector, some activation potential. And then your matrix would explain these connections here. You know, how much, if this one's activated, how much does it influence this one, each of the ones in the next layer?
Do these weights have to, like, are they just arbitrary, or do they have to add up to like one?
They're arbitrary to start out. So you start out with something random, and then as it learns, it will tune them to be whatever is correct. Now I should mention, it's very difficult to interpret what those actually correspond to. You know, what is it actually learning? So even though the computer is learning something, figuring out what it learned, which observable you should look for in your data, you know, which linear combination of variables are important, that's still something that's an active area of research.
Yeah, they use a lot of neural networks for protein folding.
Yes.
From what I understand, although they can train the computer to figure out like which pathways are the best, they don't entirely understand what it's actually doing.
That's right, and so that's why it's a little bit controversial, is because you have some black box system which gives you your answer, but to some extent you didn't really learn what's happening. So that's why this is good as a supplement in research. It's not good, I mean, it's great to have your answer, but it's also good to understand scientifically what's happening, right? So I use methods like this as sort of a way to guide intuition, right? So maybe it'll say, hey, it found that this data can be classified in these two ways, right? What that tells you is that there does exist some distinction in your data. There does exist something there. So it's worth looking into more. So even if you don't know what the function would be, it gives it to you. Anyone else?
So when you say that one layer of neurons influences the next layer of neurons, what do you mean by influences?
That's a good question. So what I mean is that this weight matrix only is between one layer and the adjacent layer. Okay, so you don't have anything from the first layer connected to the third layer, and that's very important.
What exactly is it doing to the next layer of neurons?
It's, so in this case, you're doing like an ax plus b operation, and it will give you out some vector, and if that vector is larger than the bias for the next layer, it will activate the next neuron. That's what it's doing. Yes?
I think of this process as just like fitting an arbitrary function.
Yes. Like I said, it's sort of like fitting a very high-dimensional polynomial to your data. Yeah, it's all just sort of linear algebra and fitting. But you want to know what those coefficients correspond to, and that's the hard part, is understanding physically what's happening in there. So there are some questions that come up. How many neurons should you have in the at least one hidden layer? And how many hidden layers should you have? What benefits do they offer? And so in general, there's some rule about the number of hidden layers here based on the number of training samples you have. I think this is the number of nodes in each hidden layer, the number of input neurons, number of output neurons. It's a very general rule. In reality, you set up your neural network so that it gives you the right answer, right? So if it doesn't work, you need to adjust things. There are rules though. So for instance, you generally want to have more input neurons than output neurons. You know, you want to have lots of information going into it, but extract something coarser from it. And then another way to look at it is you can taper it off. So rather than having them all be the same size, as I show here, you might have, 1,000 here, 800, 600, 100, something like that, to taper it off. And ultimately, this is for specific problems like classification. So deep learning and deep neural networks can be used for many, many things, and I want to emphasize that this is only for one application that I'm talking about. Yes?
So these like steel matrices that we talked about, do they have to be like a defined size, or can you have matrices of multiple sizes?
So in this case, the matrix size is going to be determined by your network structure. So the matrix size will depend on how many of these links you have. So we'll see a little bit more in the tutorial how you set this up and what it looks like in practice. I know that it seems like it's a lot. It seems like a lot of overhead to solve something, but we'll be using TensorFlow, which is based on Python, and a lot of it is abstracted away, and it's actually quite easy to learn how to do, I think. So let's look at the feed-forward step. So first we're going to train it with data that we understand, where we have data and we know, given all of our different bins for the outputs, which one it should end up in. So first we construct this neural network. We initialize the weights and biases to random values, and then take batches of training data. So not all of the training data at once and not one at a time, but sort of random subsets of it. You're going to feed the data forward in this matrix operation, okay? So you have your inputs, or X, your biases, and this L corresponds to the layer. You have your weights and some output Z. And Z is going to sort of be what goes into the next layer. One thing you can do is you can smooth it a little bit using this function here. So this, for instance, if you want your input to the next layer to be all between 0 and 1, for instance, it might make sense to normalize things. The other reason you want to do that is because you don't want extremely small or extremely large values just for computational reasons. The computer has a hard time representing those things, and you'll lose a lot of precision. So in the case that you get something that's really, really small, it's important to truncate it to 0 once in a while. The final output is going to be a probability vector given by what are called softmax neurons. And what that means is you put them into this function here, and for your output layer, you're going to have a probability that it ends up in each thing. So you're not saying, given this input data, it's A, B, C, or D. You're going to say probability that it's A, probability that it's B, probability that it's C, probability that it's D. And because of this softmax neuron, those probabilities end up adding up to 1. So if it's trained well, and if it truly is able to distinguish characteristics and features in data, then it will be very, very certain that it ends up in 1, and it will have very small probabilities for all of the other bins. What we're doing in order to determine the error when we're training it is we set up some error function. So here I've used a cross-entropy cost function, which is given by this. And if you look on the TensorFlow website, there are a whole host of different functions that you can use. You don't actually have to write this all out in the code. You just tell it you want to use cross-entropy, and it does it. The weights and biases are updated via the stochastic gradient descent. So you might be familiar with this method. So once it feeds forward and you get your output and you figure out what the error is, and it will be terrible at the beginning, it will be all wrong, you calculate the error for your layer, and it will be some vector. So each neuron at every point will have some error associated with it. So first, for the final layer, you're calculating it this way. So you're looking at the difference between the true value, the calculated value, and you're doing this Hadamard product based on this output vector here. And this is just the sigmoid function, the derivative of the sigmoid function. And then once you find the error vector in your final layer, you use that error to determine the error in the next to last layer. And then you use that to determine the error in the layer before that. So that's why it's called back propagation. You're propagating the error back to the beginning. And by doing that, you update the weights and biases for all of the layers this way. It's iteratively updated. So you calculate the error delta, and this tells you how to update things. Now, there's this eta parameter called the learning rate. And this is sort of, because we're doing stochastic gradient descent, you have to determine how fast are you going down the slope for your gradient descent. If you have some energy basin, or if you set the learning rate too fast, you're going to be going back and forth, but never reach your minimum. And similarly, if your learning rate is too small, you'll never reach the minimum. It'll go very, very slowly and maybe never converge. So I want to talk about an example. We're going to look at, before we start the tutorial, I'll just give this real example. For Minkowski random geometric graphs. So for the previous example, or the previous tutorial, I mean, we were looking at just regular Euclidean geometric graphs. In this case, we're going to take the first coordinate and call it time, and then update everything else accordingly. So it's really not very different. We take about 10,000 samples for each dimension, a batch size of about 1,000. We use 100 input neurons, and the reason we do that is because n equals 100. And we use these order interval abundances in the graph. So what I'm using to train it is a bunch of subgraphs, the abundance of subgraphs. So if you can see this, what I'm looking for is the number of these lengths. I guess you guys can't see very well. Let's see. So I'm looking at the number of lengths, number of diamonds, number of these types of things, everything you can think of. And I'm counting up how many there are. It's a finite size system, so there's going to be a finite number of those. And I get some distribution. the result, I'm going to have 3 output neurons, 1 for each dimension. So what I'm asking is, given some random graph, is it 2D, 3D, or 4D? This is something where there is a known analytic solution only in the case of Minkowski, which is flat space. However, it's not known what the solution is for curved space. So we want to see if we train it with only graphs from flat space, can it still infer the dimension from something more complex? Is that a coarse enough feature that we can extract it using a neural network? And the way I've tapered the hidden layers is I go from 100 down to 72, down to 48, down to 24, and then finally to 3. And I choose this as my learning rate because after some trial and error, that seemed to work pretty well. And then finally with the data, typically what you do is you take about 80% of it and use it for training, and then 20% for validation, just to make sure that your model is working. So you don't want to validate with the same data that you use to train it, otherwise it will trivially be correct. And what we see is that after about 1,300 steps, it starts to learn something. It's the update of the weights and biases jump from about 40% correct to about 70% correct classification. And then after that, it grows quite quickly up towards 100%. It's always difficult to get it to go from 98 to 99% or 99 to 99.5%. So there will be some upper bound that is determined based on sort of the add-ons to your model, I would call it. But this is what you're looking for in deep learning or supervised learning. So one thing you can construct is a confusion matrix. And what you're looking at here is, given the actual data, how well does it predict? And the reason you would construct something like this is because, for instance, you want to know that for 2D, it's predicting it correctly all of the time. The only ones it's messing up are these 3D and 4D ones. It's not confusing any of the 2D with the 4D ones, for instance. So this is a good way to determine how your classifier is performing. Then we take a look at de Sitter. So we're using a slightly different graphs now, and we see that it still works fairly well. You have a few that are wrong, but for the bulk of the time, 99.8% of the time, it's correct. And then similarly, if you use some dust space-time, then it also performs very well. So that's a simple example, and you can see in the IPython notebook what that code looks like. So I want to move right along to the tutorial now. You're going to connect exactly the same way as you did before. It's going to be set up sort of in a similar way where you can do some either easier stuff, you can do some more advanced stuff if you want. You can go through the examples which accompany these slides. You can compare them to the manual implementations, looking them up online. You can benchmark them if you want, practice benchmarking. You can go through the Jupyter Notebook to look at a basic TensorFlow program. It really is no more than 100 lines of code to do something that produces real results with real data. If you want to do something a little more challenging, you can use an eigensolver as well as the generator from the previous tutorial and measure how the number of k cycles changes with n. So as your graphs get bigger and bigger, how do these cycles converge? Do some of them grow faster than others, for instance? So this is an important question for discrete geometry. You can also look at the singular values of the adjacency matrix for small graphs like n equals 100. So if you write these to a one-line file and repeat for a whole bunch of them, then you can have some data that you can feed into the Jupyter Notebook. And then there's some more advanced tasks if you choose to do so. Can you, for instance, train it with small graphs, but then take just the leading singular values of large graphs and still extract something like the dimension? That's another option. So I'll put this I'll put these slides in the Dropbox again, and then we can do the tutorial.